Alright, looks like the recording is working. So hello everyone and welcome to another vlog on my channel. So today we will do some programming and I will actually implement the constant pool or part of the constant pool for my virtual machine. So I'm currently working on a new type of programming language, which is like a mixture of Java, Python and Lua. Yes, I think that fits it pretty well. And I'm working on the compiler and on the interpreter, and I'm working in C because I want the language to be embeddable into game engines, for example. And C is still the lingua franca of the programming scene, so you can embed C libraries in almost any language using FFI or using dynamic symbols. You can open them and call them. So yes, I'm working in C. Normally I'm doing a lot of C++, but yes, today and for this project I'm using C99 and C99. Alright, so what is a constant pool? A constant pool is a general concept used in many virtual machines, but in general it's meant that a constant pool is like a pool of constant values. So for example, if you have like a stack-based bytecode, like I have in my programming language, you can push values into the stack and you can pop values off. And you need some way to submit constant immediate values to the bytecode. So let's take a look at how Java handles this. Let's switch over to Java. So we have a square method here, and we can see our bytecode generated over here. Going to zoom in a little bit. So, all right, let's call this f for function, and let's just return a simple constant scalar value like 10, scalar of 10. And as you can see, we are using a push instruction to push the value 10 onto the stack. Push byte integer push, I guess. That's probably what it means. So it pushes the value 10 onto the stack, but let's push a double value. So let's change the return type to double and wait until it compiles. And as you can see, we have a new method here. Push long or double from the runtime constant pool wide index. Wide index because in Java, a stack slot on the stack consumes 4 bytes, and doubles and long consume 8 bytes. So they're using 2 stack slots to store the data. Let's do it with a float, which is 4 bytes, and IEEE 754 floating point value. So you can see we have instruction here, LDC, push item from runtime constant pool with the index of 7. So a constant pool is generally a hash map which has an index, or it could also be an array, it doesn't matter, but you can imagine it like a hash map. And it has some integer as a key, and as a value it just has a constant value. It could be a float, an integer, a string too. And this of course depends on the implementation. I don't know exactly how it's handled in Java, but I need a similar concept for my bytecode. So let's investigate another thing. So let's do this again with an integer. And as you can see, here we're pushing the value 10 directly onto the stack. We are not loading it from the constant pool. If you're like loading from the constant pool using LDC, what we are doing, we are like going to the constant pool, looking where the value from our key is, and then we're pushing that onto the stack. But we won't do this over here. We pushing the value directly. In assembly language programming, this is called an immediate value. So the value is encoded within or with the instruction. That depends on the architecture, of course. All right. So if we have our 10, we can see we push it directly. But what if we try to push the maximum value of an integer? That would be this for 32-bit signed integers. We have a 4, or yes, that should be correct. And as you can see, now we are also using the load constant pool instruction. So there is some kind of restriction which values you can push. And I don't actually want to investigate further how Java does this because I don't care. I also already have my restrictions. So let's take a look at the code. So in my virtual machine, bytecode instructions are 32-bit wide, and they're stored in host byte order. So if we have like a big endian system and the bytecode file is stored in a little endian, we have to convert them. Okay, but if we take a look over here, we have 32 bits and we have 7 bits of opcode. So 7 bits are used for the opcode so that the virtual machine knows which kind of instruction to actually execute. Then we have 1 bit for the mode. There's like 2 modes. One mode is the first one here with a 24-bit immediate signed integer. And there's a second mode, but it's not yet implemented. So I was just thinking about implementing it. I was just playing around. So I'm not quite sure what mode 2 will be, but I have reserved 1 bit to switch modes. Maybe we will need it. Maybe I will actually remove it. I don't know yet. And you can see we have a 24-bit integer value, assigned integer value. So that basically means we can do the same as in Java. If we have like a small value like 10, we can push it using the immediate value over here. Let's take a look at some constants here. We can, wait, I have to change one thing. Change font size, yes, with mouse wheel. So I can scroll in that you can see the code better. All right, so if our value x is within these 2 values, so if x, no, it's not an absolute value, so let's if x is within 2, we can append a minus because the sign bit is already set in this value, but just to make it more clear. So that basically means that x is in with like set notation from here to here, like this, for example. Yes, and if x is outside of this range, so if like all of the integer and float values are 64 bits in my programming language, so we have like a double for float and we have an int for we have an int64t for int, and that basically means that we can of course can't of course push like a 64-bit immediate value. If we do like 64 divided by 24, you can see we need 2.6 instructions to like push a 64-bit immediate value, and it's not acceptable. So in this case we use the constant pool. And if we take a look at the instructions already implemented, we can see we have more of them. Here's our LDC instruction, which loads a value from the constant pool and then pushes it onto the stack. And here's our integer push, which pushes 24-bit immediate value. So we don't have a float push. We can't push a float because a float doesn't fit in 24 bits. And of course we could like divide the bits of the float and push it part by part, but that sounds like really error prone and I don't want to do it. So for small values we have iPush. And for common immediate values we have overloads. So for example, if I want to push the value 0, which is like really common in programming, you often use the value 0. We have a dedicated instruction for that. We have iPush 0, which just pushes 0. We also have that for 1 and 2, which are also used a lot. For example, in a loop, if you increment a variable using like I++ or ++i, you effectively need to push the value 1 if you don't have an increment instruction. I don't know if you will have an increment and decrement instruction, maybe we will see. And we also have iPush M1, which just pushes -1. And let's take a look. We will see that Java has these dedicated instructions too. So let's return -1. And you can see we have an instruction iConst M1, push ins constant. And this is basically exactly the same. So Java compiler checks the value when you want to like load, and then replaces the generic push instructions using a specified one, if it applies in this case. Let's take a look. I think it should also have one for 0. Icon 0, yes it has. Okay, so Java does the same. And we also have these for floats. Float 0, 1, 2, and we have also float 0.5 because it's also used a lot for example, for division, and also we have float -1. So we have these for floats too. So in general, if we want to push an immediate value x first, we want to take a look, is x like, in this case, 0, 1, 2, or -1? If it is, we use one of these instructions. These are the fastest. Then, if x is not one of these instructions here, we check if x is within our 24-bit signed integer range. If x is within that range, we use the iPush instruction using x. So we push and we convert x into a 24-bit signed integer and push that value directly. But if x is outside of this range, so if x is, for example, int64 max or int max in the runtime, then we use our LDC instruction and load the value from the constant pool. So what is a constant pool in general? I already have defined a struct constant pool here. So we have our pointer to a record, and a record is basically a union which represents a single stack element. So let's take a look. Stack, computer science. Let's take a look at some examples. So I haven't really prepared any good examples for this video, and I probably should. I will think about better video like examples in the future and all. So let's take a look. A stack. So yes, that's fine. We can use this. Okay, no, I just want the image. So yeah, it's kind of blurry, but we have our stack here, and this is our stack pointer on the left. The number here is the stack pointer in our case, and it's defined in the virtual machine over here. You can see it's also of type record, stack pointer. And if we push a value, the stack pointer is incremented in our case, and if we pop, it's decremented. So let's take a look. Push, increment stack pointer, pop, subtract, or decrement stack pointer. On real hardware, so like on x68, 64 CPUs, the stack actually grows downwards. So if we push, we actually subtract from the stack. But that's in hardware, and we don't care what hardware does because we are working in a virtual environment or custom virtual machine. So we have our stack over here, and stacks are represented by records. So like each of these slots is a record which can either be an int, a float, a char, a bool, or an object reference for the garbage collector, or it can also be an unsigned int. But my programming language, which is called Neo, does not have an unsigned integer. It just has int, float, char, and bool. And this is just for internal reasons to keep, for example, object tags. So we will use this later. And in this case, we have our record, and we have just an array of these records in our constant pool because we just want to load a value from the constant pool using a specific index. For example, 0 would be the first element in a constant pool, which can be whatever we inserted there. And we have another array of tags. As you can see, this union is not tagged or not discriminated. That means that we don't know which of these fields is active at runtime. So a union is like a struct but with overlapped addresses, and we need to store which element is currently active. We need that information because when we do bytecode validation, we want to validate that if we want to load a float, then we also need to check if our runtime type is also float. Because if not, there could be horrendous errors everywhere. So we actually need this type information. So why would I not create a new struct? Like, let's do it. Typedef struct t-record t, and yes, let's do it like here. Record r tag t tag 8 bits. So we save some memory, 16 bytes. It doesn't matter in this case because it's 64-bit and the compiler will pad and align, but yes, why not like this? And this is like a general problem called it's called array of structs versus struct of arrays. Yes, and I could have had it like that, but if we load the value, we will never check the type. If we take a look at the VM code for LDC, we do a push, we unpack the 24-bit immediate, which is an index into the constant pool in this case. So we have a constant pool index, 24 bits wide. We unpack it, and then we push the int value. But we do not check the type. This int is like a reinterpret cast or like a memcopy. We will just copy the memory. We do not care about the type. The type checking is done inside the bytecode validation, which is not yet done. I do not check types for now. I will implement this later. So this basically means that we don't need this information at runtime. If I go back to our header, we don't need the tag information at runtime. And if I would have kept an array of these over here, I would waste a lot of, I would waste 8 bytes of cache, of data cache, each time I access one of these records, because the CPU reads in memory in cache lines, not like in single bytes. It does a whole cache line read, and I don't want to waste values. And constant pool accesses are fairly common, so I don't want to keep this data around. I want to keep this in a separate array. And if we read a cache line of records, I will also read in other records which we might need in another instruction. There's also another reason why this is a better design choice in this case, because, for example, let's say I actually want to implement SIMD in the JIT compiler later, single instruction multiple data, which are like special instructions which can process multiple data or multiple values once at a time. We can take a look at this. Let's do a little C program, and let's see at let's take a look at GCC. If GCC is good at autovectorization. Autovectorization is the process of vectorizing scalar code into using SIMD instructions. So let's do a simple add function. Let's add some floats. Let's do float dsd const float source. And what we want to do, let's create a simple loop. Let's add 4 floats, which could correspond to a vector 4 in game development, for example. dst I plus equals source I. Alright, let's take a look. So without optimization, we have a lot of clobber and a lot of code which is bad. So let's say optimization level 3. Alright, but the problem is we're still using scalar instructions. Move SS stands for move scalar single precision, and move SD for double. So it still uses scalar code. It does not use SIMD code. Why? Why does it not use SIMD instructions? We have like move APS, move UPD. We have lots of SIMD instructions, and the problem is that these pointers could overlap. These could point to the same memory, and the SIMD instruction would not emit the correct result. So in this case, we want to use the C restrict keyword on one of these pointers. And you can actually see that that the compiler vectorized our code. Move UPS means move unaligned packed single precision floating point values. In this case 4, because XMM registers, which are like SSE registers, are 128 bits wide. And inside of these registers, we can, in this case, compute 4 32-bit float values. So move UPS, move unaligned, because our address here is not aligned to 16 bytes. You can get a little performance boost on, I would say, generally most CPUs. It does matter that much today, but on most CPUs you can get a little performance boost if you use the aligned version, move APD. But then this address must be dividable by 16 by the register size. So in this case, we can't guarantee that. And then we use add PS, add packed single precision floats. So we do all 4 at once. and then we move the result back. And this is an example of SIMD code. And as you've heard, I've talked about alignment of these memory addresses, and that's exactly what we can do if we have our data in linear memory addresses. I can actually store some SIMD constants in a constant pool and align them to some specific boundary at runtime, and then use really efficient instructions to load them into these SIMD registers. This was my thought process behind having the data without the discriminators. To make this more interesting, we can use the AVX2 flag, which is Advanced Vector Extensions 2. These are some special CPU instructions, and as you can see, our code changed a little bit. We have this V here, which stands for VEX version. VEX is a different encoding scheme, and yeah, this is like a more flexible version. We have like 3 operand instructions here. We can it gives more room for the register allocator, and it could enable better performance. But yeah, in general, in my JIT compiler, autovectorization is already really hard, so I just probably will use basic SSE. But AVX is really nice. You also have these 256-bit YMM registers, and they can do 8 floats once at a time. And there's even AVX512F, which can do 16 floats at a time. So my CPU unfortunately does not have these instructions. I have a Threadripper 3970X. Let's take a look. LS CPU. Yeah, we have a Threadripper, 32 cores. And let's take a look at these extensions here. We have extensions here. We have MMX, we have SSE, which are like the XMM registers. We have also AVX, like Haswell cores have AVX. We have SSE string stuff, AVX, 64-bit conversion stuff, 16-bit float conversion. We have SSE, misaligned SSE, and we should have AVX2 and BME. AVX2. The AVX2 instruction set is like AVX. It does not add any new registers, but it just it basically adds new integer instructions, and bit manipulation instructions are also really useful. So I'm getting a little off topic here. I will probably do a video about SIMD anyway, but I just wanted to explain the rationale behind using this kind of data design for the virtual machine. Okay, so we have our constant pool, and yeah, that's exactly how it works. So what I want to do now, I want to write a little test. I want to write a unit test. This video will probably be renamed like implementing a constant pool, but that's not correct. I just talked about the implementation, and yes, so let's do a test. Let's do a little test. Let's see if our LDC instruction works. And to be honest, I haven't checked. I haven't tried to make it work. So let's test it. So I haven't tested the LDC instruction. So I just implemented it last night. So let's see if it works. As you can see, we're also using computed Go to dispatch tables for the VM. And yes. Okay. So let's do some tests. I'm actually using C++ for unit tests because it's easier and it's faster. It's more productive, but the runtime and the compiler itself does not need C++. I'm using C++20 and I've written a lot of modern C++ in my game dev stuff. So I'm using modern, or at least semi-modern C++ here too. So let's test the LDC instruction. I will just copy paste this. And what we will do an LDC from constant pool index 0. So we will try to load the first value from the constant pool. And we of course need to initialize the constant pool first. So let's create a new std array of a record t. And yeah, thanks GitHub Copilot. Const pool, yes. And what we also need is we need the tags. Exactly. Damn, it's really, really good. Okay, so let's create a new record t, and we want, why not do a float? Because float comparisons are s. Let's do an int, and let's do null 0x. Let's do 1, 2, 3, 4, 5. Okay, and now we need a tag, so we will do an int. So this maps directly to this, and that means that they need to have the same size, of course. So in this case, it would actually be smart to do it like that. And this is our testing LDC. Okay, we have our stack, and we need to initialize our const pool. This is not that clean. I will probably create like an VM initialize method later. So let's take a look. vm.constpool.p, which is like the pointer to the data, is const pool data, and tags is tag data, and length is the size. And of course, the VM should check it, but let's validate that they have the same size. So yeah, should I don't know. No, let's don't do it, because it has to be the same size, because we specified it in the template here. Okay, alright, so we have our constant pool set up, and if we execute our LEC, we should get this value on the stack over here. So let's, maybe I need to adjust these, but let's run the tests and see. Yeah, it worked immediately. Nice. It's unexpected to have code work like you intended, like you thought it would on the first try, but it's really nice. Let's do a breakpoint. Take a look at the values. Let's take a look at the const pool. First element has our value. Let's take a look at the stack. This first value does not have our value, because the first value is a padding. It's not used actually for the stack. The first one is actually the value which is used, which is pushed into. This is also a different design choice. I will maybe show this in another video. So we have our value here. I have to admit that when a unit test runs immediately, it's kind of sus. I have to insert an error and see if it actually is run. Yes, now it fails. Yeah, it fails. Okay, let's reverse and run. And now it works. Okay, really nice. So yes, that's the basic overview on how the constant pools work from a virtual machine. And yeah, this is also my second video on the channel, so I will not quite sure on which direction my channel will go, but I will just continue making some programming videos, and I will see what you viewers like and whatnot. So yes, I hope that you get a little insight on this video, and maybe you also found it interesting, and I wish you a wonderful day, and I hope to see you soon. Goodbye.